Stellar nursery birth unfolds in molecular clouds where gravitational collapse fragments vast gas reservoirs into multiple protostars. The Sun forming within dense stellar clusters where dozens of young stars ignite simultaneously from the same cosmic material. The Eagle Nebula and similar star-forming regions demonstrate how stellar birth proceeds through collective rather than solitary processes. Gravitational instabilities creating stellar siblings that share common chemical compositions and formation timescales within chaotic environments where stellar interactions shape early stellar evolution. Molecular cloud fragmentation operates through gravitational collapse that creates hierarchical clustering patterns. Dense cores within larger structures subdividing into smaller condensations that eventually become individual protostars. These fragmentation processes naturally produce binary and multiple star systems as gravitational dynamics favor stellar pairing during the accretion phase when protostars remain embedded within their natal molecular material. Stellar formation physics predisposing toward binary rather than solitary stellar outcomes. Protosolar nebula formation occurs within this clustered stellar environment where neighboring protostars influence disk structure and planetary formation processes through gravitational perturbations and radiation pressure effects. The early solar system develops while embedded within a stellar cluster containing hundreds of young stars, whose proximity creates dynamical interactions that modify planetary disk evolution and determine long-term orbital stability for planetary systems forming simultaneously within the same stellar nursery. Gravitational interactions between forming protostars create complex orbital dynamics that determine which stellar pairs remain bound as binary systems and which become gravitationally unbound through three-body interactions and energy exchange processes. These early dynamical interactions establish the initial orbital parameters for binary star systems, while creating the conditions that will eventually lead to binary separation through subsequent gravitational encounters with other cluster members. Stellar accretion disks intersect and interact when protostars form in close proximity. Disk material transferring between stellar companions while creating complex accretion flows that influence both stellar masses and disk compositions. These disk interactions affect planetary formation by altering the distribution of solid materials and volatile compounds within individual stellar systems. Early stellar interactions determining the chemical composition and mass distribution of materials available for planetary accretion. Early stellar clustering creates environments where stellar encounters occur frequently enough to modify binary orbital parameters through gravitational perturbations. Close approaches between binary systems and single stars causing orbital energy changes that can either tighten or widen binary separations. These stellar encounters establish the dynamical framework within which binary star evolution proceeds. Early cluster dynamics determining which binary systems remain tightly bound and which evolve toward eventual separation. Isotopic homogenization across stellar cluster members occurs through early stellar wind interactions and supernova enrichment from massive cluster members, neighboring stellar systems sharing similar isotopic signatures that reflect common formation environments and chemical evolution histories. This isotopic similarity between cluster members provides observational signatures that allow identification of stellar siblings even after cluster dispersal separates originally neighboring stars across galactic distances. Stellar cluster dispersal begins within the first few million years as stellar winds and supernova explosions from massive cluster members disrupt the gravitational binding of the stellar cluster. Individual stars and binary systems acquiring random velocities that carry them away from their formation regions. This cluster dispersal process determines which binary systems survive intact and which become separated through differential galactic motion and continuing gravitational encounters with field stars. Brown dwarf companions form through the same fragmentation processes that create stellar companions. Failed stars achieving insufficient mass for hydrogen fusion while remaining gravitationally bound to their stellar primaries. These substellar companions occupy a continuous mass spectrum from planetary mass objects through brown dwarf masses up to red dwarf stellar masses. Binary formation processes creating companions across this entire mass range through gravitational collapse and accretion during the early phases of stellar formation. Observational evidence for stellar clustering during solar formation comes from isotopic analysis of meteorites that preserve chemical signatures of early stellar nuclear synthesis from nearby massive stars. Short-lived radioactive isotopes in meteoritic materials requiring proximity to supernova sources during solar system formation. These isotopic signatures provide direct evidence that the Sun formed within a stellar cluster containing massive stars whose evolution influenced the chemical composition of solar system materials. Distruncation effects occur when stellar companions interact gravitationally with circumstellar disks. Binary star formation creating tidal truncation of disk material that limits the radial extent of planetary formation regions. These distruncation effects influence planetary system architecture by determining the maximum orbital distances at which planets can form, while affecting the total mass of solid material available for planetary accretion within truncated disk regions. Some believe stellar cluster dissolution explains the current isolation of the solar system from other stars. Cluster dispersal separating originally neighboring stellar systems through galactic orbital motion and gravitational encounters with massive molecular clouds. Others suggest that the Sun formed in a less dense stellar environment where binary formation remained less common, stellar isolation resulting from formation conditions rather than subsequent evolutionary processes. Stellar mass segregation within forming clusters creates spatial separation between high-mass and low-mass stars. Dynamical evolution concentrating massive stars toward cluster centers, while lower-mass stars and binary systems migrate toward cluster peripheries. This mass segregation affects binary star evolution by influencing the frequency and strength of gravitational encounters that determine binary orbital evolution and eventual binary survival or dissolution. Chemical tagging techniques identify potential solar siblings through detailed spectroscopic analysis of stellar abundances. Stars with identical chemical compositions potentially originating from the same molecular cloud and stellar formation episode as the Sun. These chemical identification methods provide observational approaches for locating solar siblings that have dispersed throughout the galactic neighborhood while maintaining chemical signatures of common origin. The irony of stellar nursery birth lies in its social nature. The Sun forming within stellar communities that shaped its early evolution, yet remaining isolated in the contemporary galaxy. Stellar formation creating temporary stellar families that disperse through galactic evolution, while leaving only chemical and dynamical signatures of their common origins embedded within stellar properties and planetary system architectures that preserve evidence of early stellar interactions. Binary formation through gravitational dance emerges as the natural outcome of stellar birth processes. Molecular cloud collapse creating rotating systems that fragment into multiple condensations whose orbital motion establishes gravitational partnerships between stellar companions. Angular momentum conservation during gravitational collapse creates binary orbital motion as collapsing material transfers rotational energy into orbital energy. Stellar formation physics favoring binary outcomes over solitary stellar formation through fundamental conservation laws governing rotating gravitational systems. Hierarchical fragmentation operates through gravitational instabilities that create binary systems at multiple scales. Molecular cloud cores subdividing into stellar pairs while these pairs form within larger multiple star systems that contain dozens of gravitationally bound stellar components. These hierarchical binary structures demonstrate how gravitational collapse naturally produces complex stellar architectures where binary formation occurs as nested gravitational systems within progressively larger gravitational groupings. Close binary formation occurs when gravitational collapse creates stellar pairs with orbital separations measured in astronomical units. Tightly bound systems where stellar companions remain within planetary disk regions and interact gravitationally with forming planetary systems. These close binary systems experience strong tidal interactions that influence both stellar evolution and planetary formation through gravitational perturbations that modify disk structure and planetary orbital dynamics throughout the early phases of stellar system evolution. Wide binary formation creates stellar pairs with orbital separations measured in thousands of astronomical units. loosely bound systems where stellar companions orbit beyond planetary formation regions, yet remain gravitationally connected through weak long-range gravitational forces. These wide binary systems prove more susceptible to disruption through external gravitational perturbations, while maintaining gravitational binding over millions of years despite their large orbital separations and correspondingly long orbital periods. Mass ratio distributions in binary systems reflect the fragmentation physics operating during stellar formation. Gravitational collapse preferentially creating binary companions with similar masses rather than extreme mass ratios. This preference for similar mass binary companions results from fragmentation processes that divide available mass approximately equally between binary components. Stellar formation physics, creating binary mass ratios that cluster around equal mass configurations while avoiding extreme mass disparities. Orbital eccentricity evolution proceeds through gravitational interactions that modify binary orbital shapes over time. Initially, circular orbits becoming eccentric through three-body gravitational encounters with other stellar systems, and through internal dynamics involving circumstellar disk interactions. These eccentricity evolution processes affect binary stability by increasing orbital velocities at periastron passage, while reducing gravitational binding energy through orbital energy redistribution during close approaches. Stellar encounter rates within forming clusters determine binary survival probabilities through the frequency of gravitational perturbations that can disrupt binary orbital motion. High stellar densities increasing encounter rates while creating environments where binary disruption becomes more probable. These encounter statistics establish the evolutionary framework within which binary systems either survive or become disrupted through external gravitational influences operating during the cluster dispersal phase. Binary orbital decay occurs through various mechanisms including gravitational wave radiation for very close binary systems and tidal friction for systems with stellar companions in contact or near-contact configurations. These orbital decay processes cause binary separations to decrease over time, while increasing orbital velocities and reducing orbital periods. Eventual stellar merger becoming possible for the closest binary systems whose orbital evolution proceeds toward direct stellar contact. Circumstellar disk interactions create additional binary evolution mechanisms through disk binary gravitational coupling that can modify binary orbital parameters during the early phases when stellar companions retain substantial circumstellar material. These disk-binary interactions affect both stellar and planetary formation by transferring angular momentum between binary orbital motion and disk rotation, while creating spiral density waves that influence disk structure and planetary migration. Multiple star system formation extends binary formation processes to create gravitationally bound systems containing three or more stellar components, hierarchical triple and quadruple systems forming through successive fragmentation episodes during molecular cloud collapse. These multiple star systems exhibit complex orbital dynamics where gravitational interactions between multiple stellar components create long-term orbital instabilities that can lead to stellar ejection or binary formation through dynamical evolution. Kozai mechanism operation in hierarchical systems creates periodic oscillations in binary orbital eccentricity and inclination through gravitational perturbations from distant stellar companions. These Kozai cycles causing dramatic changes in binary orbital configurations over timescales of thousands to millions of years. These dynamical cycles affect binary stability by creating phases of high orbital eccentricity that increase the probability of close stellar approaches and potential binary disruption or stellar merger. Some believe binary formation represents the dominant mode of stellar formation, with most stars forming initially as binary systems that subsequently evolve through various disruption mechanisms, while others suggest that binary formation frequencies depend on local environmental conditions within molecular clouds and stellar clusters. The universality of binary formation processes remains debated, but observational evidence clearly demonstrates that binary formation represents a common outcome of stellar formation. Tidal synchronization processes cause binary stellar companions to become tidally locked with orbital periods equal to stellar rotation periods. Gravitational tidal forces synchronizing stellar rotation with binary orbital motion over timescales that depend on stellar structure and binary separation. These tidal evolution processes affect stellar magnetic activity and stellar evolution through modified rotation rates and internal mixing processes that influence stellar structure and stellar lifetime. Binary mass transfer occurs when one stellar companion evolves to fill its Roche lobe and transfers material to its binary partner. Mass transfer creating complex evolutionary pathways that can dramatically alter both stellar masses and stellar evolutionary timescales. These mass transfer processes create observational signatures including X-ray emission and nova outbursts while demonstrating how binary evolution can modify stellar properties through direct mass exchange between stellar companions. The irony of binary gravitational dance lies in its ubiquity yet instability. Gravitational forces that create binary partnerships also containing within themselves the mechanisms for binary disruption. Stellar formation preferentially creating binary systems through gravitational collapse while embedding these same systems within dynamical environments that promote binary dissolution through continuing gravitational interactions. Binary formation representing temporary gravitational partnerships that reflect both the creative and destructive aspects of gravitational dynamics operating across stellar formation and stellar evolution timescales. Nemesis hypothesis emerges from periodic extinction patterns preserved in the geological record. Mass extinction events recurring approximately every 26 million years in cycles that suggest gravitational perturbation of cometary orbits by an undiscovered stellar companion orbiting the Sun at vast distances. The regularity of extinction timing implies astronomical forcing mechanisms operating on galactic timescales. Hypothetical binary companion creating periodic comet showers through gravitational disruption of Oort Cloud stability during closest approach phases of highly elliptical stellar orbits. Paleontological extinction data reveals temporal clustering of major biodiversity crises, including the Permian-Triassic, Cretaceous-Paleogene, and Ordovician-Silurian extinction events whose timing suggests external astronomical triggers rather than purely terrestrial causation mechanisms. These extinction patterns span hundreds of millions of years while maintaining statistical regularity that exceeds random chance. Geological evidence pointing toward periodic astronomical phenomena that influence terrestrial biological evolution through extraterrestrial impact events and climate perturbations. Oort Cloud perturbation mechanics demonstrate how distant stellar companions could gravitationally disturb the vast spherical reservoir of comets surrounding the solar system. Stellar passages through outer cometary regions destabilizing comet orbits and sending increased numbers of comets toward the inner solar system. These gravitational perturbations operate through tidal forces that overcome the weak gravitational binding of distant comets. Stellar companion approaches creating comet showers that persist for millions of years following each perturbing passage. Impact crater chronology on Earth and Moon preserves evidence for episodic bombardment periods, when impact rates exceeded background levels by factors of several times normal impact frequencies. Crater dating suggesting periodic increases in extraterrestrial impact events that correlate with biological extinction timing. These bombardment episodes indicate enhanced delivery of comets and asteroids to Earth-crossing orbits through gravitational perturbations of small body populations by external astronomical influences. Galactic oscillation cycles create additional periodic forcing mechanisms as the solar system orbits through the Milky Way galaxy. Vertical oscillations through the galactic plane, exposing the solar system to varying gravitational fields and cosmic ray intensities that could trigger biological extinctions. These galactic motion cycles operate on timescales of 60 to 70 million years, while creating encounters with molecular clouds and spiral arm regions that modify the local astronomical environment surrounding the solar system. Theoretical orbital calculations for hypothetical stellar companions explore the range of possible orbital configurations that could produce 26 million year periodicity. Nemesis orbit models requiring aphelion distances of 1 to 3 light-years with orbital eccentricities approaching unity to generate appropriate perturbation timing. These orbital dynamics calculations demonstrate that gravitationally bound stellar companions could exist at distances beyond current observational detection limits While maintaining sufficient gravitational influence to affect Oort Cloud stability, red dwarf companion scenarios investigate low-mass stellar objects as potential Nemesis candidates. M-dwarf stars providing sufficient gravitational influence to perturb comet orbits while remaining observationally inconspicuous due to extremely low luminosity and infrared emission characteristics. These red dwarf models address observational constraints by proposing stellar companions with masses approaching the hydrogen burning limit, yet remaining detectable only through sophisticated infrared astronomical surveys and gravitational perturbation analysis. Brown dwarf alternative models propose substellar companions with masses below the hydrogen burning threshold. Failed stars retaining sufficient gravitational influence to affect outer solar system dynamics while avoiding detection through conventional stellar survey techniques. These brown dwarf scenarios require masses of several Jupiter masses to several dozen Jupiter masses. Objects occupying the mass regime between giant planets and red dwarf stars where observational detection remains challenging despite significant gravitational effects. Statistical analysis of extinction timing examines the significance of apparent periodicity in mass extinction events. Fourier analysis and spectral techniques investigating whether observed extinction patterns exceed random fluctuations in biological diversity and extinction rates. These statistical studies address the question of whether extinction periodicity represents genuine astronomical forcing or results from incomplete geological records and statistical artifacts in paleontological data compilation. Alternative extinction mechanisms propose terrestrial and solar system internal causes for periodic mass extinctions, including volcanic activity cycles, climate oscillations, and solar luminosity variations that could generate extinction periodicity without requiring external stellar companions. These alternative models investigate whether periodic extinctions can result from internal solar system dynamics or terrestrial geological processes operating on million-year timescales rather than external astronomical perturbations. Observational search programs utilize infrared astronomical surveys and astrometric measurements to investigate potential stellar companions within the outer solar system. Systematic searches for point sources with appropriate motion characteristics and infrared emission signatures that could indicate brown dwarf or red dwarf stellar companions. These search efforts include analysis of WISE infrared survey data and Gaia astrometric measurements that provide unprecedented sensitivity to faint astronomical objects throughout the solar neighborhood. Some believe the Nemesis hypothesis provides the most plausible explanation for extinction periodicity based on statistical analysis of paleontological data, while others suggest that extinction patterns result from terrestrial processes or statistical artifacts rather than astronomical forcing mechanisms. The debate over extinction periodicity continues as paleontological and astronomical evidence accumulates through improved geological dating techniques and astronomical surveys. Comet shower modeling investigates the expected signatures of Nemesis-induced perturbations, including enhanced comet discovery rates, unusual comet orbital characteristics, and increased meteor shower activity that would result from gravitational disruption of Oort Cloud stability. These theoretical predictions provide observational tests for the Nemesis hypothesis through analysis of contemporary comet populations and historical records of unusual astronomical phenomena. Galactic tide interactions with hypothetical stellar companions create additional complexity in orbital evolution calculations. Milky Way gravitational fields influencing the long-term stability of wide binary orbits, while potentially causing orbital precession and eccentricity evolution that could modify perturbation timing over geological timescales. The irony of the Nemesis hypothesis lies in its proposal of cosmic partnership driving terrestrial destruction. Stellar companionship creating biological catastrophe through gravitational dynamics that connect galactic evolution to terrestrial evolution. Hypothetical binary relationship generating mass extinctions that paradoxically create evolutionary opportunities through biological crisis. Stellar twins sharing responsibility for both creation and destruction of terrestrial life through gravitational interactions that operate across astronomical distances and geological time to influence the course of biological evolution on Earth. Early solar system chaos unfolds through binary stellar interactions that reshape planetary formation, while influencing asteroid and comet distribution throughout the protoplanetary environment. Gravitational perturbations from stellar companions, creating dynamical instabilities that modify planetary accretion processes and determine final planetary system architecture. Binary companion gravitational effects generate orbital resonances, planetary migration episodes, and disk structure modifications that establish the contemporary solar system configuration through early dynamical evolution shaped by stellar multiplicity. Protoplanetary disk truncation occurs when binary stellar companions gravitationally limit the radial extent of circumstellar material. Tidal forces from stellar partners creating sharp outer boundaries in planetary formation regions, while preventing planetary accretion beyond truncation radii. These disk truncation effects determine the maximum orbital distances for planetary formation, while concentrating solid materials within smaller radial zones that enhance planetary accretion rates through increased surface density of planetesimals and dust particles. Planetary migration acceleration results from binary companion gravitational perturbations that modify disk density distributions and create non-axis symmetric gravitational potentials. Stellar companion effects driving rapid inward or outward planetary migration through enhanced gravitational torques between planets and disk material. These migration processes can relocate giant planets from outer to inner orbital regions or eject planets entirely from stellar systems through gravitational interactions amplified by binary stellar dynamics. Asteroid belt architecture preservation requires specific dynamical conditions that prevent complete dispersal of small body populations. Binary stellar interactions potentially creating the gravitational environment necessary for maintaining asteroid concentrations within specific orbital zones despite planetary migration and disk evolution. These dynamical protection mechanisms operate through resonance structures and gravitational shepherding effects that stabilize asteroid orbits against disruptive perturbations from migrating planets. Kuiper belt formation proceeds through binary-influenced disk evolution that concentrates trans-Neptunian objects within specific orbital regions. Stellar companion effects creating the dynamical conditions necessary for preserving cold classical Kuiper belt populations while generating scattered disk objects through gravitational scattering events. These outer solar system structures preserve evidence of early binary interactions through their orbital distributions and dynamical characteristics that reflect complex gravitational evolution. Late heavy bombardment triggering may result from binary stellar interactions that destabilize asteroid and comet populations approximately 700 million years after solar system formation. Delayed gravitational effects from stellar companion perturbations creating the enhanced impact flux that shaped lunar and planetary crater records. These bombardment episodes represent dynamical evidence for continuing binary evolution effects that influence inner solar system evolution long after initial planetary formation completion. Giant planet orbital configuration develops through binary-mediated dynamical evolution that creates the current Jupiter, Saturn, Uranus, Neptune architecture. Stellar companion gravitational effects contributing to planetary orbital spacing and eccentricity. Distributions through complex gravitational interactions during the gas disk dispersal phase. These planetary configurations preserve dynamical signatures of early binary interactions that shaped planetary system architecture through multi-body gravitational evolution. Trojan asteroid populations form through binary-influenced gravitational dynamics that create stable libration zones around planetary orbital positions. Stellar companion effects modifying the stability boundaries of Trojan regions while influencing the capture efficiency of small bodies into co-orbital motion with planets. These Trojan populations provide dynamical evidence for binary stellar effects on small body orbital evolution throughout solar system history. Irregular satellite capture occurs through three-body gravitational interactions involving planets, satellites, and binary stellar companions. Stellar companion gravitational effects facilitating the capture of small bodies into bound orbits around giant planets through energy dissipation during close gravitational encounters. These irregular satellite systems preserve evidence of early solar system dynamical evolution, when stellar companions could influence planetary satellite formation through gravitational assistance. Comet reservoir establishment requires specific dynamical conditions for preserving volatile-rich objects at large heliocentric distances, binary stellar interactions creating the gravitational environment necessary for Oort Cloud formation, while preventing complete dispersal of cometary materials through external stellar perturbations. These comet reservoirs represent the most distant gravitational signatures of early binary interactions that shaped outer solar system structure. Zodiacal dust production results from collisional evolution of asteroid and comet populations, whose orbital distributions reflect early binary-influenced dynamical processes. Stellar companion effects creating the small body configurations that generate contemporary interplanetary dust through ongoing collisional grinding and cometary outgassing. These dust populations preserve information about early solar system dynamical evolution through their spatial and temporal distribution patterns. Some believe binary stellar interactions provide the most plausible explanation for several puzzling aspects of solar system architecture, including planetary orbital configurations and small body distributions, while others suggest that planetary system evolution can proceed through internal gravitational dynamics without requiring binary companion effects. The role of binary interactions in solar system formation remains debated as dynamical models explore various formation scenarios. Planetary spin characteristics may preserve evidence of binary-influence formation processes through angular momentum distributions that reflect gravitational torques from stellar companions during planetary accretion. Binary effects potentially explaining unusual planetary rotation states and obliquity values through gravitational interactions during the late stages of planetary formation when stellar companions remain gravitationally significant. Ring system formation around giant planets could result from binary-influenced tidal disruption of satellites and captured objects. Stellar companion gravitational effects enhancing tidal forces during close approaches, while creating the dynamical conditions necessary for satellite disruption and ring material production around giant planetary systems. The irony of early solar system chaos lies in its creative destruction. Binary stellar interactions generating dynamical instabilities that disrupt simple planetary formation while simultaneously creating the complex gravitational environment necessary for producing the diverse planetary system architecture observed today. Stellar companionship driving both constructive and destructive processes that shape planetary formation through gravitational chaos that ultimately creates ordered planetary configurations from initial dynamical disorder. Binary evolution creating solar system complexity through gravitational interactions that transcend simple single-star planetary formation scenarios. Gravitational ejection mechanisms separate stellar twins through close encounters and dynamical instabilities that cause binary star separation via gravitational slingshot effects and energy exchange processes operating within stellar clusters and galactic environments. Three-body interactions between binary systems and passing stars create gravitational perturbations that can unbind stellar companions by transferring orbital energy to kinetic energy. Stellar encounters providing sufficient energy input to overcome gravitational binding and send former binary companions on divergent galactic trajectories. Energy exchange during stellar encounters operates through gravitational dynamics that redistribute kinetic and potential energy among interacting stellar systems. Close approaches between binary pairs and field stars creating momentum transfer that can either tighten or completely disrupt binary orbital configurations. These energy exchange processes follow conservation laws that require precise energy and angular momentum accounting during gravitational encounters. Stellar interaction outcomes determined by encounter geometry, stellar masses, and relative velocities during closest approach phases. Three-body problem dynamics govern the complex gravitational interactions when single stars encounter binary systems. Analytical solutions becoming impossible for general three-body configurations, while numerical integration reveals chaotic behavior and sensitive dependence on initial conditions. These three-body encounters create unpredictable outcomes, where small changes in encounter parameters can dramatically alter final stellar trajectories. Binary disruption versus binary survival depending on precise encounter geometries that determine energy transfer efficiency. Stellar cluster dispersal accelerates binary separation through multiple weak encounters that gradually modify binary orbital parameters over millions of years. Cumulative perturbations from numerous distant stellar passages eventually providing sufficient energy input to unbind wide binary systems. These dispersal processes operate through statistical mechanics where large numbers of weak gravitational encounters produce systematic orbital evolution. Cluster environment determining binary survival rates through encounter frequency and typical encounter velocities. Hyperbolic trajectories result when gravitational encounters provide sufficient energy to exceed escape velocity from binary orbital motion. Disrupted stellar companions acquiring galactic velocities that carry them away from their formation regions at speeds determined by encounter energetics. These ejection velocities create observable signatures in stellar kinematics, where high-velocity stars may represent former binary companions that experienced violent gravitational encounters during cluster dispersal or subsequent galactic evolution. Kozai-Lidov cycles in hierarchical triple systems create periodic oscillations in binary orbital eccentricity that can drive stellar companions to extremely close approaches. These dynamical cycles potentially leading to stellar merger or binary disruption through tidal forces during periastron passage. The Kozai mechanism operates through gravitational perturbations from distant third bodies that cause coupled evolution of orbital eccentricity and inclination, creating long-term dynamical instabilities that affect binary survival over millions of orbital periods. Galactic tide effects gradually separate wide binary systems through differential gravitational forces exerted by the Milky Way galaxy's mass distribution. Tidal forces becoming significant for binary separations exceeding several thousand astronomical units, where galactic gravity can overcome weak binary binding. These tidal disruption processes operate over hundreds of millions of years as binary systems orbit through varying galactic gravitational environments. Galactic structure determining the long-term stability of the widest binary configurations. Stellar mass loss through stellar winds and mass transfer can reduce binary gravitational binding sufficiently to cause binary separation. Mass loss reducing the gravitational potential well that maintains binary orbital motion, while potentially providing sufficient energy for binary unbinding. These mass loss mechanisms become particularly important for binary systems containing evolved stars, where stellar winds and planetary nebula ejection can remove substantial fractions of stellar mass over relatively short evolutionary timescales. Close encounter statistics within stellar clusters determine binary disruption rates through the frequency and strength of gravitational perturbations experienced by binary systems. Dense cluster environments creating high encounter rates that promote binary disruption, while sparse stellar environments allow binary survival over longer timescales. These statistical encounter rates depend on cluster stellar density, velocity dispersion, and cluster dynamical evolution that determine the probability distributions for binary single-star encounters. Runaway star formation occurs when binary systems experience asymmetric supernova explosions that impart substantial recoil velocities to surviving stellar companions. Supernova kicks, providing impulsive velocity changes that can unbind binary systems while creating high-velocity runaway stars observable throughout the galactic disk. These supernova disruption events demonstrate how stellar evolution within binary systems can create binary separation through explosive mass loss and momentum transfer during core collapse events. Gravitational wave radiation causes orbital decay in very close binary systems containing compact objects. Energy loss through gravitational wave emission causing binary separation to decrease over time until eventual merger occurs for the closest binary configurations. These gravitational wave effects become significant only for binary systems with orbital periods measured in hours or days, demonstrating how Einstein's general relativity affects binary evolution through space-time curvature and gravitational radiation damping. Some believe binary separation represents the natural evolutionary outcome for most binary systems, formed in stellar clusters due to environmental perturbations and internal dynamical evolution, while others suggest that binary survival depends critically on initial orbital parameters and local stellar environment characteristics. The relative importance of various binary disruption mechanisms remains debated as stellar dynamics simulations explore different cluster evolution scenarios. Stellar collision outcomes during close binary encounters can result in stellar merger rather than binary separation. Direct stellar collisions creating single merged stars while eliminating binary orbital motion through complete gravitational capture and stellar envelope mixing. These collision processes become important in dense stellar environments where encounter velocities remain low enough to allow gravitational capture rather than hyperbolic flyby trajectories. Planetary system effects during binary disruption can scatter or eject planetary companions through gravitational perturbations that destabilize planetary orbits. Binary separation events creating chaotic planetary dynamics that may eject planets from stellar systems or dramatically modify planetary orbital characteristics through impulsive gravitational perturbations during stellar companion separation. The irony of gravitational ejection lies in its utilization of the same gravitational forces that created binary partnerships. Gravitational attraction generating both binary formation and binary destruction through encounter dynamics that demonstrate gravity's dual role as both binding and separating force. Stellar twins sharing common origins, yet becoming separated through gravitational interactions that reflect the chaotic nature of gravitational dynamics operating in multi-body stellar systems where gravitational creativity and gravitational destruction operate through identical physical mechanisms. Brown dwarf companions hide in darkness throughout outer solar system regions, where their dim infrared emissions escape astronomical observation. Failed stellar objects with masses below the hydrogen-burning threshold, remaining gravitationally bound yet observationally elusive due to extremely low luminosity and thermal emission characteristics. These substellar companions occupy the mass regime between giant planets and red dwarf stars. Objects with masses ranging from 10 to 80 Jupiter masses that achieve deuterium burning but fail to sustain hydrogen fusion reactions that characterize true stellar objects. Infrared emission characteristics of brown dwarfs create observational challenges for detection within the solar system. These objects radiating primarily in infrared wavelengths with effective temperatures ranging from several hundred to several thousand Kelvin depending on mass and age. Brown dwarf luminosities decrease over time as gravitational contraction energy dissipates through radiative cooling. Older brown dwarfs becoming progressively fainter and more difficult to detect against the infrared background radiation from zodiacal dust and galactic sources. Orbital dynamics calculations demonstrate that brown dwarf companions could remain gravitationally bound to the Sun at distances of hundreds to thousands of astronomical units. Wide orbital configurations allowing substellar companions to maintain stable elliptical orbits with periods measured in hundreds of thousands to millions of years. These distant orbital positions place potential brown dwarf companions beyond the detection limits of most astronomical surveys while maintaining sufficient gravitational binding to prevent disruption by galactic tidal forces. WISE infrared survey limitations reveal the observational constraints that allow brown dwarf companions to remain undetected within the outer solar system. All-sky infrared surveys achieving sensitivity limits that exclude brown dwarf detection beyond specific distance thresholds, depending on brown dwarf mass and effective temperature. These sensitivity limitations create detection boundaries within which brown dwarf companions could exist while remaining below current observational detection capabilities. Proper motion signatures provide potential detection methods for brown dwarf solar system companions through astrometric measurements that reveal orbital motion against background stellar fields. Brown dwarf orbital motion creating detectable position changes over multi-year observation baselines for sufficiently bright infrared sources. These astrometric detection techniques require sophisticated measurement precision and long-term monitoring programs that can distinguish orbital motion from random proper motion of background field brown dwarfs. Gravitational perturbation effects from brown dwarf companions could influence outer solar system dynamics through long-range gravitational forces that modify comet and asteroid orbital evolution. Substellar companion gravitational effects, creating detectable signatures in small body orbital distributions and long-period comet characteristics. These gravitational influence patterns provide indirect detection methods for brown dwarf companions through analysis of outer solar system dynamical evolution and anomalous orbital behavior. Thermal evolution models predict brown dwarf cooling curves that determine infrared luminosity as functions of mass and age. Substellar cooling calculations providing theoretical frameworks for predicting brown dwarf observational characteristics at solar system formation, age of 4.5 billion years. These thermal evolution predictions establish brightness expectations for brown dwarf companions while accounting for deuterium burning effects and atmospheric composition variations that influence infrared emission spectra. Formation mechanisms for brown dwarf companions include gravitational collapse fragmentation during early solar system formation and capture processes involving substellar objects formed in nearby stellar systems. Brown dwarf formation pathways determining mass distributions and orbital characteristics for potential solar system brown dwarf populations. These formation scenarios predict different brown dwarf properties including composition, orbital parameters, and satellite systems that could provide observational discrimination between formation mechanisms. Atmospheric composition modeling for brown dwarfs reveals complex chemical equilibrium calculations involving hydrogen, helium, methane, ammonia, and water vapor that determine infrared spectral characteristics. Atmospheric chemistry affecting brown dwarf observational signatures through molecular absorption features that create distinctive spectroscopic identification criteria. These atmospheric models provide theoretical frameworks for brown dwarf spectroscopic detection and characterization through infrared astronomical observations. Magnetic field generation in brown dwarfs occurs through dynamo processes similar to stellar magnetic field production. Substellar magnetic fields creating radio emission signatures that could provide alternative detection methods for brown dwarf companions through radio astronomical observations. These radio emission mechanisms operate through charged particle acceleration in brown dwarf magnetospheres while generating detectable radio signals that complement infrared detection techniques. Binary brown dwarf systems demonstrate that substellar objects can form gravitationally bound pairs through fragmentation processes similar to stellar binary formation. Brown dwarf binary systems providing analogues for potential brown dwarf stellar companion configurations that could characterize solar system substellar companions. These binary substellar systems establish observational precedents for brown dwarf companion formation while demonstrating brown dwarf orbital dynamics and evolution in binary configurations. Some believe brown dwarf companions represent the most plausible explanation for hypothetical solar system stellar companions due to their low observational detectability and appropriate gravitational influence characteristics, while others suggest that comprehensive infrared surveys have achieved sufficient sensitivity to exclude brown dwarf companions within most plausible orbital configurations. The debate over brown dwarf companion existence continues as infrared astronomical capabilities improve. Deuterium abundance measurements in brown dwarf atmospheres provide age and formation diagnostics through deuterium burning rates that depend on brown dwarf mass and thermal evolution history. Deuterium depletion creating observational signatures that reveal brown dwarf evolutionary status and formation timescales. These deuterium burning signatures provide astronomical tools for characterizing brown dwarf properties and distinguishing between different formation scenarios. Satellite system formation around brown dwarfs creates additional observational signatures through circumsubstellar disk evolution and satellite orbital dynamics. Brown dwarf satellite systems potentially providing detection opportunities through gravitational perturbation effects and infrared emission from circumsubstellar material heating processes. The irony of brown dwarf stealth lies in their substantial mass yet minimal luminosity. Failed stars achieving significant gravitational influence while remaining observationally inconspicuous due to nuclear burning failure. These almost stars demonstrating how stellar formation can produce massive objects that hover at the boundary between stellar and substellar classification, while maintaining gravitational significance that exceeds their observational prominence. Brown dwarf companions, potentially sharing solar system space while remaining hidden in infrared darkness that conceals their presence from astronomical detection, despite their substantial gravitational influence on outer solar system evolution. Oort Cloud architecture reflects binary heritage through cometary reservoir structure and dynamics that preserve evidence of past binary stellar interactions in orbital distribution patterns. The spherical shell of comets surrounding the solar system maintaining dynamical signatures of early stellar companion gravitational effects that shaped comet population characteristics. The Oort Cloud's vast extent, reaching halfway to the nearest stars, creates a gravitational memory bank where past binary interactions remain encoded in comet orbital parameters and spatial distributions that reflect the gravitational history of solar system stellar multiplicity. Cometary orbital inclination distributions demonstrate isotropic characteristics that suggest gravitational stirring by external stellar perturbations. Random orientation of comet orbits indicating past gravitational interactions with stellar companions, or passing field stars that randomized initially flattened comet distributions. These isotropic orbital patterns contrast with inner solar system comet populations that retain preferential orbital orientations. Outer Oort Cloud isotropy providing evidence for external stellar gravitational effects that modified comet orbital characteristics through binary companion interactions. Two-component Oort Cloud structure reveals distinct inner and outer comet populations with different orbital characteristics and formation histories. Inner Oort Cloud comets maintaining slightly flattened distributions, while outer Oort Cloud comets exhibit completely spherical symmetry. This structural dichotomy suggests different evolutionary processes affecting inner versus outer comet populations. Binary stellar interactions potentially explaining the transition between partially organized inner regions and completely randomized outer regions through differential gravitational stirring effects. Galactic tide interactions with Oort Cloud populations create periodic perturbations that send long-period comets toward the inner solar system. Galactic gravitational fields producing systematic comet flux variations as the solar system oscillates through the galactic plane during its orbital motion around the Milky Way center. These galactic tide effects operate on timescales of tens of millions of years, while creating observable variations in comet discovery rates and long-period comet orbital characteristics that reflect galactic influence on solar system comet populations. Stellar encounter statistics predict comet perturbation rates based on local stellar density and velocity distributions. Close stellar passages providing impulsive gravitational kicks that destabilize comet orbits and create observable comet showers lasting millions of years following each stellar encounter. These encounter predictions establish theoretical frameworks for understanding historical comet flux variations, while providing observational tests for stellar encounter frequency and stellar companion interaction effects on Oort Cloud evolution. Comet capture mechanisms during binary formation could explain Oort Cloud mass and extent through gravitational interactions that captured cometary material from circumstellar regions around binary stellar companions. Early binary evolution creating comet exchange processes that enhance solar system comet populations through material transfer from stellar companion circumstellar regions. These capture scenarios suggest that Oort Cloud comets may include materials formed around binary stellar companions, rather than exclusively solar system formation products. Hills Cloud formation represents intermediate comet populations between Kuiper Belt and outer Oort Cloud regions. These transitional comet reservoirs potentially preserving more detailed signatures of binary stellar interactions through orbital characteristics that reflect specific binary configuration parameters and binary evolution timescales. Hills Cloud dynamics provide observational windows into past binary interactions through comet orbital element distributions that encode information about stellar companion masses and orbital characteristics. Dynamical fossil evidence for binary interactions appears in contemporary comet orbital distributions through statistical analysis of orbital parameter correlations and anomalous orbital characteristics that exceed expectations for purely galactic perturbation effects. These dynamical fossils preserve information about past binary interactions in observable comet populations, while providing retrospective constraints on binary companion properties and binary evolution histories through statistical analysis of comet orbital characteristics. Comet composition variations may preserve chemical signatures of formation in different circumstellar environments. Isotopic and molecular composition differences between comet populations, potentially indicating origins around different stellar systems during early binary formation episodes. These compositional variations provide chemical forensics for binary interaction histories while establishing observational tests for comet capture scenarios and material exchange processes during binary stellar evolution. Numerical simulation results for binary-influenced Oort Cloud evolution demonstrate how stellar companion gravitational effects modify comet population characteristics over millions of years. N-body integration calculations revealing the dynamical pathways through which binary interactions create observable signatures in contemporary comet populations. These simulation studies provide theoretical frameworks for interpreting observational data, while predicting specific signatures of binary evolution in comet orbital distributions. Observational surveys of long-period comets search for statistical signatures of past binary interactions through analysis of comet orbital element distributions, aphelia directions, and orbital period clustering that could indicate gravitational focusing effects from former stellar companions. These observational programs utilize large comet databases to identify subtle statistical signals that exceed random expectations while providing empirical constraints on binary interaction scenarios and stellar companion properties. Some believe Oort Cloud structure provides compelling evidence for past binary stellar interactions based on dynamical modeling and observational comet statistics, while others suggest that Oort Cloud characteristics can result from galactic perturbations and stellar encounter effects without requiring binary companion scenarios. The interpretation of Oort Cloud evidence for binary heritage remains debated as observational datasets expand and dynamical modeling sophistication improves. Comet shower modeling predicts enhanced comet flux episodes following binary companion close approaches. Theoretical calculations establishing expected comet delivery rates and duration of enhanced comet activity that could create observable signatures in terrestrial impact records and comet discovery statistics. These shower predictions provide observational tests for binary interaction scenarios while connecting comet dynamics to terrestrial geological and biological evolution through impact event correlations. Retrograde comet populations exhibit orbital characteristics that may indicate capture from stellar companion systems or gravitational interactions that reversed initial prograde orbital motion. Retrograde comet dynamics providing additional constraints on binary interaction scenarios and comet population evolution. These retrograde populations represent statistical anomalies